This lecture is going to cover vocal fold vibration, and we'll talk about some of the mechanics of how that occurs. So the first thing we need to think about is what are the parts, what are the steps in the process. So we have 5 parts, they're numbered here, and you can see that the first one is vocal fold adduction. You're very familiar with that at this point. We also have talked about subglottal pressure, which is usually the same as alveolar pressure, comes from the lungs through the trachea and builds up below the adducted vocal folds. The vertical phase difference is what we're going to refer to here in number 3, and that is the fact that the bottom part of the vocal folds opens first and then the top part follows. So sort of if you consider the speech language pathology version of the itsy bitsy spider, you can mimic it with your hands. So your hands will open at the bottom part first, and then the top opens, and then they close at the bottom. So I'm trying to get an angle where you can see. Okay, so this is really an imitation of how the vocal folds respond to that subglottal pressure. Okay, that's called the vertical phase difference. So if you looked at it in a vertical plane, you'd see that they're not opening and closing at the same time. There is the bottom first and the top. The fourth point here is the concept that the center of the vocal folds will open before the periphery, the outside. So we call that the horizontal phase difference, and I will review that in an upcoming slide. But we have to remember that these two things are happening at the same time. So the vocal folds have very complex movement from the bottom to the top, from the middle to the outside, and then back again. And then on top of that, we have the mucosal wave. Remember when we talked about the jello on the plate, so the Schwabelkuecheli? So the plate moves at a different frequency than all the reverberating jello on top of it, and so that creates that wave, and that adds a lot to the complexity of the sound wave that is generated. So we have all these things going on at the same time. That's why when we speak, we don't just have a pure tone ooh. We have, all kinds of harmonics reverberating and working in concert with the vocal tract to create different resonances and frequencies. In the next slide, we have another sort of step-by-step scenario of what happens. You can see we have our laryngeal, vestibule, ventricle, and subglottal space. We indicate here, these are the vocal folds that are adducted, right? And it's muscular forces that cause them to come together, right? And they also then want to stay together because of surface tension. Remember we talked about the alveoli and the intrapleural space in respiration. Those had surfactant in there. Well, because the mucous membranes lining the laryngeal cavity also have some moisture to them, there is that surface tension. So once they're together, they kind of need a little bit of extra energy to physically pull them apart, because their natural law of physics would be to keep them together. The other thing to think about is gravity. Gravity will also encourage the vocal folds to close. And how does that work? So if you think that it's opened at the top and then it's closing at the bottom, if the bottom's connected, it doesn't have that subglottal pressure pushing up now. So this is part of the cycle where the pressure is lower. So we've released that pressure, the bottom is together, and because there's less pressure, gravity is going to pull it down. Okay. So then the next thing that happens is you have compressed the lungs and pressure builds up, and so then subglottal pressure is going to build up in this space. So that's what blows them apart. Okay. And then once they've come apart, recoil forces cause them to want to come together. So it's the same thing that we're talking about with relaxation pressure in the respiratory muscles. You have these muscles, and then they want to go back to their original shape or form. So that's happening bottom to top. And then the fifth part here is that I'm going to assume that you guys know and understand about Bernoulli forces and the Bernoulli effect, which you probably learned about in physics. So we know that when the air moves more rapidly through that area, it creates negative pressure, so that the vocal folds, because that air has puffed through the laryngeal opening, the glottis, that it's going to pull them together because of increased negative pressure in the space between the vocal folds, which will cause a type of suction that will cause it to go together. And so these 5 things keep cycling back and forth, creating this vibratory cycle that repeats itself. The next slide, I won't go through step by step, but you can stop the video if you want to right now and look at this from one little incremental change to another, so that you can get a good mental image of what's happening with those vocal folds. On the next slide here, we have, let me make the picture go away. I think it's supposed to go away. In the next slide, goodness, I'm sorry, technical difficulties, I don't want to waste time. The horizontal and vertical phase are shown here to give you the idea that they're happening at the same time. And it's hard for us to kind of conceptualize, well, wait, bottom to top and then center to outside, how is that happening all at the same time? But it is. And you can see in the horizontal phase, if you look from the bottom, start at A at the bottom and move upwards, you can see that the glottis is closed, it opens from the center, continues opening, eventually it is fully abducted, and then it begins to close from the outside toward the center again. And it is actually slightly to the posterior end of the glottis where that opening actually starts. So the question about the horizontal phase difference, a lot of times students have a little trouble understanding it all. So I just went ahead and sort of wrote it out here so that you can read through it and get the idea. Again, I won't read it for you, but you could pause the video and read it. But that's kind of a summary of what I've tried to describe here. Next slide. So now we want to just remind ourselves the glottis. Oh yeah, the glottis is the opening actually. So in this case, A would be a large glottis, B would be medium, C would be small. The D picture is in a small glottis, and when it is small, sometimes it's partially closed. The little triangle at the base of the D illustration here is sometimes called the whisper triangle. So you do have air opening, but it's not as open as some of the other cases. The final one has no glottis. Remember, glottis means the opening. So for that reason, there is no opening in that one. Okay, so the next slide, we have this title, vocal fold length. So what do I mean by that? Well, the whole vocal folds are, they go from the thyroid to the arytenoids. But in practice, we often talk about the effective vocal fold length. So the part that's actually vibrating and touching is really the effective length of the vocal folds that are vibrating. So what I wanted you to notice with this other illustration in the corner here is that the part that's vibrating is usually the membranous part. As you recall, the cartilaginous part of the vocal folds is in the posterior, closest to the arytenoids. And so if we're talking about effective vibrating vocal fold length, this is really the part here that we're referring to. Okay, so moving on. Let's talk about stiffness and tension of the vocal folds. This is an important concept because it has a lot to do with how we modulate pitch and loudness. So we have two terms here that we're going to define. So in the green arrows here refer to stiffness, and what stiffness, if you wanted to give a definition for it, it's how much force is required to displace the tissue. So the amount of force required for the displacement. The longitudinal tension, the one in the yellow there, is referring to how much force is required to change the length. So tension really you can think of in terms of like a guitar string that you're tightening the screw and lengthening the string. So what I also want to draw attention to here is that, so we have the anatomical drawing there, and then we have sort of the schematic view. We have, remember, the thyromuscularis is in the lateral portion, and then the medial would be the thyrovocalis. And then this orange part right here is representing the vocal ligament, which is integrated with the muscle, but it's also the, remember, the upper thickened margin of the conus elasticus. So how these things operate has a lot to do with raising and lowering pitch and to some extent loudness intensity. So we'll get into that in an upcoming video, but this lays the groundwork for understanding that. So to contrast rigidity and tightness, really rigidity, we're talking about the displacement. If something is rigid, you can't displace it. And then tightness would be more that tension aspect. So if you could imagine for the rigidity side, imagine that you have a curtain, like a stage curtain made out of a thick fabric, okay? And so if you can compare that thick stage curtain fabric to something really thin like chiffon or some other really light fabric, if you apply force to the stage curtain, it's going to take quite a bit of force to displace that curtain. However, if I have chiffon or like shears for your windows, if there's just a light force, maybe even the wind, or you could blow on it, that would displace it. So the chiffon is not very rigid. It has quite a bit of amenability. Anyway, it will move easily, whereas the thicker, or maybe if you had something like corduroy or something, that's not going to move as easily. So that would be a more rigid fabric in this case, but we're talking about vocal folds now. So how much they move when an applied force is occurred. So when a force is applied. So the higher the stiffness, the less they move when force is applied. So if you have stiff vocal folds, that's going to affect the quality of your voice. Tightness is like stretching a guitar string. And oops, I'm having technical problems here, sorry. Okay, so that's an easier metaphor to imagine, but if you pull it, it stretches. What happens when you stretch a guitar string and make it tighter? The frequency goes up, the pitch goes higher, right? So the thing to remember is something that we call cross-sectional mass. Now we did have a reference to that in your labs, or there will be if you're seeing this before the lab. So if I have a rubber band, that's a thick rubber band, or I have this elastic right here. So here's a piece of elastic, okay? If I stretch it, well, first of all, before I stretch it, if I were to take a cross section, just cut it right here, here, let me do this. If I were to just cut it along its medially, you would see that it's about this thick, right? So there's a certain thickness to it. I don't know if I think you see this. So there's a thickness. You can get a good idea what that is. Now, if I stretch it, you see that it's longer now because I've increased the tension along that elastic. But also, if I were to make a cut right here, it would be thinner right here. And that is the cross-sectional mass. So the actual mass of the section of elastic that I have marked out here would be the same whether it's not stretched